here are some seats just in between. Maybe you can squeeze in the rows. Might be more comfortable than on the stairs. But anyway, looks great. Thanks for your attendance. So I think let's go. I am Marcus. I work as a software architect for Active Group. We do software development, we do consulting, we offer trainings, and our specialty and our strength is that we use functional programming in all the projects that we do. And additionally, we run the biggest German-speaking blog on functional programming, so you should check that out. One of our clients manufactures microchips. So manufacturing microchips or semiconductors or wafers is quite a complex process. It contains many steps, needs many different machines, processes, and systems, and it builds the basis of a very large and heterogeneous IT infrastructure. Just to give you an idea, once the wafers that are sliced out of these large ingots enter the factory, there are many iterations in building up the structures that make out such a microchip. Is involved lithography, etching, heating, many steps, chemical processes, mechanical processes, until in the very end the microchips fall out. And in many wafer fabs, it's the case that each step is performed by different machines, by different manufacturers. Process engineers, they are the ones who are designing such a process and have to monitor this process. And when we got hired, the situation for a process engineer is the following. Whenever anything goes wrong, whenever something goes wrong in the production, a process engineer had to log on manually to equipment controllers, to some legacy applications. They had to look on network shares. They had to query databases, and they had to look on the message bus just to see what went on during the time the production failed. And collecting all this information is, of course, a tedious task. And it was a lot of work, and often it didn't even yield results because it's not that easy to correlate all the information from these different sources into one coherent picture. So again, the reason for this pandemonium of the large and heterogeneous IT infrastructure is caused by the complicated process that is needed for manufacturing microchips. And in our case, because of the age of the wafer fab, we are also talking about different states of modernization. So we faced all kinds of versions of operating systems and even communication technologies ranging from serial ports up to high-speed networking. So this was the situation when we got on board. And what actually started as a working title for the project stuck, it's often the case. Panacea. Panacea is a figure of Greek mythology. She is the goddess of universal health. And that was the goal of the project, to universally heal the brokenness and the cumbersomeness of the system, just to fix it. And this is what we came up with. Instead of the many different systems that the poor process engineer had to log on, in our system they can use like 3 main applications to view all the data. We have a Kibana for discovering and searching in front of a long-term event storage. We use Elasticsearch for that. We have Grafana for on top of time series databases like Prometheus or InfluxDB for metrics and for monitoring the system health and also like performance indicators of the fab. And we have a third one. This is a custom-built alerting system called Smart Alarms. I'm going to talk about that later. Yeah. So these 3 views collect everything and hide the Pandemonium behind them. We've achieved that by doing the tedious work of collecting all the information that occur in these systems. Yeah. So now it's our turn, our system's turn, to take the logs, look on the network shares, query the databases, and listen to the message bus. What we have in the center, where we bring all that data together, is our real-time stream processing system. Our system that we use is based on Riemann. Riemann is an open source stream processing software that is written in Clojure. It's configurable and programmable in Clojure. And that's just our thing. Clojure is a functional programming language that runs on the Java virtual machine. And it's actually one of the programming languages that we use most in our projects. And that also fits well with IT infrastructure, because much existing software in enterprise IT actually runs on the JVM as well. So we can always hook in there. Our system needs many different input sources to collect all the data. So we use some Logstash-based input sources from reading the log files that are located on network shares. We use also Filebeat and Lumberjack for those hosts that send their log files to our system over the network. An important and central entry point for our client is the TIPGO rendezvous messaging bus. Anyone heard of that? Anybody use that? It's like a quite old common message bus that is used in fabrication, in automation of different fabs. And that also is like a important and grown infrastructure for our client. In fact, they use many different message encodings on the TIPGO bus, so we also had to write all those encoders for that. Additionally, we import from SQL databases and even have some more modern Industry 4.0 standards like open platform communications in our portfolio. And once we process that, the output destinations, our system is also capable of collecting data and preparing that data for many different output destinations. We use Elasticsearch for long-time storage. We support different time series databases. So we started with InfluxDB, weren't quite that happy, dabbled a little bit with Graphite, and now are consolidating to Prometheus. Panacea is also capable of writing back to the TIPGO message bus. Yeah, that's again important for our client, because then we can trigger other automations again in turn. And of course, just unavoidable in enterprise IT, we have to write to databases. So maybe sometimes we can get rid of those. Yeah, and as already mentioned, we have those web applications over here. It's Kibana, it's Grafana, and we can also add random other third-party software in our design. We are quite flexible. A very important part of our system is alerting. Yeah. We have to alert the process engineers when some conditions or problems occur during manufacturing. Since we use Grafana and we use Prometheus, we can use all the alerting mechanism that those applications provide. So usually what that looks like, in those metrics-based alerts is that they are based on some kind of aggregation. Like, for example, if a resource is more than 90% used for the last 5 minutes, that's worth an alert, so then send the alert. Currently, we provide some predefined alarms we developed with the process engineers that we provision to those systems, or that we provision to Grafana and to Prometheus Alertmanager. But also the users can build their own dashboards and add their own alerts, their own alert rules. But we realized that that's not enough for our client. Our process engineers needed more, that the aggregations that were just not enough for what they needed. So that's where we came up with the second custom alerting mechanism that hooks directly into the real-time stream processor. So it does not alert on aggregations. It does alert on events that hit the stream processor. And again, that worked out to be a very important feature. We've achieved all this by doing what we at Active Group are best at, applying the principles of functional software architecture. There is a well-known pattern in functional programming that is called the imperative shell and the functional core. So where the application core is functionally pure and all the side effects, everything that has to do with the world that has like state or imperative programming is pushed to the outside shell. There is a related software architecture pattern in object-oriented programming, and that's what I show here. It's called hexagonal programming. It's called hexagonal architecture. And also it's called like ports and adapters architecture pattern. And actually we prefer that more, since the name hexagonal is just derived from the graphics, from the kind it is drawn. But there is actually nothing that would justify like 6 part of that pattern or ever. I could have drawn it just with different amounts of corners. So the ports and adapters architecture is a very important software pattern that allowed us to build that system. So the important ideas of this architecture are that we have the separation of the application core, and that every interaction with the outside world goes through well-defined ports and uses adapters and the implementation of those adapters. The benefit is that the separation makes the application core testable independently. Tests, tests, tests. And also, the adapters are also like can be changed independently. Maybe you need to change one of those adapters especially for testing, just for mock testing, or for a different deployment environment. And all these adapters can hook up to the ports as seen fit. And this is great. It's very useful. So, like recommendation for you, it's very useful for you to think in this pattern about your application. And of course, our application fits well inside there. So our functional core is the real-time stream processing, and all of our many input sources and the output destinations are connected via ports and are implemented as adapters. And this is our functional core. It supports filtering of events, transformation, enrichment of events. It accumulates information. It combines the events from all kinds of different input sources. It is able to correlate that information that is often not findable by our poor process engineer just alone. And it supports data aggregation, and it supports projections. And as I mentioned, we've implemented that on top of our stream processor Riemann. But actually, we are even independent of Riemann. Yeah, we are actually able to switch stream processors because we added another layer of abstraction. Because for event matching and event processing, we developed a domain-specific language. So here you can see a small example of that domain-specific language. I'm going to explain everything in that code. So this is closure code. Yeah, some parents disclosure code. Everything that has DSL/ in front of it, that is a namespace identifier. So that means that functionality is in the namespace DSL that is important in this small example namespace. And what this conveniently named function wait for event does, it waits for an event that follows this pattern. The next few lines describe the pattern, describe how the event this function waits for should look like. And then the last line here is when an event is found, this is what should happen. So the first line of the pattern expects the event to have a field subject. The value that is with the field subject in the event should match the regular expression. This is a regular expression enclosure that starts with production, equipment, alarm report, and some arbitrary rest. And the value of this field, if it exists in the event, is bound to a variable named a subject that can be used in the body. So just a convenient way to also to match and to bind in one statement. The next part of the pattern actually describes that there should be a field data in our arriving event, and with a bracket it says that data in turn is again like composed data. So in the data there is again expected like a key value data structure that should include the field CMD, yeah, short for command, and that should be bound to alarm report. If that hit, it's bound to CMD. Yeah, same for the other three fields here. So in the nested data structure below data, there should be alarm state. Yeah, that should be 1, and there should be alarm ID. Here's nothing given, so alarm ID can be arbitrary. Every value matches, but it must be there. Yeah, and same for alarm text. Can be arbitrary, but the field must be there. Yeah. There's also a way to describe optional fields with the question mark in front. Alarm severity is an optional field below the nested data structure, and it can be absent. The event would match anyways. So when wait for event waits for this event, and if it's there, yeah, we make an alarm consisting. This is a constructor we build. We make an alarm with the fields alarm ID, alarm text, alarm severity, and then we hit our DSL again to process that event we just generated. And what happens in the end is that the process engineer gets an alert. So what we have here is a fast and expressive and powerful domain-specific language that fits exactly what we need. Yeah. We implement the DSL as a monad, yeah, and therefore we have just another abstraction layer. And with how we use those DSLs, with how we use the monads to implement our functional core, like also be like the business logic, yeah, that is what the process engineer is interested in. Yeah, we add functionality that does not exist in plain Riemann and in plain ELK stacks. Yeah, and with that, we are actually independent of Riemann, because we can switch out our stream processor. Like, for example, we could move to Kafka if our client's IT policy would demand it. One of our ideas was that our domain-specific language should be easy enough and clear enough for the process engineers to use by themselves. They should be able to develop the filters they need by their own, writing this concise code. But that didn't really come to fruition until now, except some rare engineers that dabble with it. We saw that even if the language is like small and understandable, it's still a learning curve. And again, these process engineers, they needed like at least to set up a development environment. If you write code, you need a syntax checker, or you need some environment to run your tests that it works. And that was just too hard and too cumbersome for most process engineers, especially since they are experts in some other domain. They have to get to have the wafer fab running, so that's their business. They don't have time for that. So what we did for them instead, we created a nice graphical user interface on top of some subset of our DSL that the process engineers can use. And that looks something like that. This is now we come back to our custom real-time alerting system. The engineers, they can set up their alerts graphically. They don't need to write DSL code, and these alerts can be based on events that directly flow through our stream processor. And here's an example of how that looks like, what our engineers can do. So on the left-hand side here, they can add some event matching. So what our UI gives them, it selects some interesting event properties, so they can choose the fields they want, and they can give the values. They give constants, they can give regular expressions, and if a hit is found, then they can specify what to do with that hit. So then we have some alarm actions, like the usual stuff. We have some alarms monitor, that's like a dashboard that collects all these alarms. They can email, they can SMS, usual stuff. And what they also can do, they can like build custom messages. And in these custom messages, they can use variables that come out of the event. So they can actually write useful error messages, useful alert messages that contain the actual information they need by using the values from the events they match on. And looking at this interface, you can actually see the DSL behind it. The pattern and what happens with that. And that system is a huge success. This is an actual quote of one of the process engineers that after we've rolled out our smart alarm system. The alarms save our bacon daily. We get alarmed by the system and can fix the errors before the operators in the wafer fab even notice the problems. Producing microchips is a high-stakes endeavor. It's expensive. Wasted wafers and defective chips during production burn so much money. Our process engineers, they fear a so-called daily delivery meeting. It sounds innocent, but this is like a high-stakes meeting where the managers hold the engineers responsible for production failures. And thanks to our system, most of the problems don't even get noticed by the managers, because the process engineers can fix these problems like beforehand. So that's quite a testimonial for our system. The deployed system is huge. Currently, it consists of about 35 containers that run on a handful of different servers. The only reasonable way for us to manage that is using functional DevOps. Instead of manual multi-step process, it has a single step. It can be performed automatically and is repeatable and it scales. We create many of our own containers with Nix, NixOS, an operating system, respectively, package manager that is purely functional. Again, with us, it's all about functional. That is purely functional and takes into account all needed dependencies in a transparent and reliable and reproducible way. And the reproducible part is most important. We orchestrate with Docker Compose. And we are quite lucky that we still can manage and host everything under our own supervision. We do not have to rely on company IT services. We do not have to use some managed container environments or managed long-time storage and stuff like that. We can innovate, we can try things out, we have a very quick turnaround in case of problems, because we just don't have to file tickets against corporate IT and possibly waiting months until some bug gets fixed, or waiting for new features that require software updates. In some of our other projects, we didn't have that supervision, and that was never good. So here's the numbers on the current system. Yeah, it ingests data from more than 20 different input sources. It outputs data to 8 different output destinations. It processes about 3,500 events per second. It stores about 200 gigs in Elasticsearch, and it stores about 5 gigs metrics per day. To wrap up, yeah, I want to share some random points, some lessons learned and future work. I just want to mention that shortly. So we learned the hard way that we should make sure that we get the same load in the test system as we actually have on production. So all the production events need to pass through the test system just to make sure that we don't hit performance problems once we deploy to production. Of course, usually, as well as in our case, the test system is not that strong. Production systems are always often stronger, but that's like an even better test. Yeah, so if it works well in our test system, we can be sure it works perfectly and smoothly once in production. And of course, there are ways to keep the test systems in bound. We have way shorter retention policies in our test system, just a couple of days, maybe just a couple of hours for our large processes. We also added some self-healing properties. Yeah, self-healing software is excellent. Yeah. Riemann emits some internal metrics about the health of its system. Yeah, about the speed the processes, the events can get processed through Riemann. And we listen to that output, and we then just temporarily disable certain streams that make a huge load and that are not needed. Yeah, of course, we negotiated with the process engineers what streams we can cut for a short amount of time. And that works just like an electrical breaker in case of some current surge. Small idea, but we like what we see so far. When can it happen? Yeah, like when can a stream malfunction? If one of our output destination doesn't respond. Yeah, if something doesn't take the events we want to output from us, then we have to cut it. And with our breaker implementation, that works excellent. And another improvement we are currently working on is that we are adding inverted indices or reverse indices to our DSL matching algorithm. Yeah, that will again increase the performance of our matches and will avoid many unneeded match attempts, and improve resource usage even better. Yeah. And again, this is the next point that makes us even more independent from the underlying stream processor. Yeah, if we even take care of event matching ourselves, of inverting indexes. Here's a list of links I want to share. Yeah, our open source closure utilities. Yeah, for closure in general, active closure, and for our logger implementation and our Riemann library in particular. And the links to some of the software packages and application I've mentioned. This list is not complete and does not want to be complete. Yes, and now I'd like to thank you very much for your attention, and I am looking forward to your questions. Thanks.